Hello there. I was going through my old diagrams to get an idea what video I wanted to make next, which is now this video, and I came across this diagram. So I have these voltage regulators. They're called a L7805. I got them from an electronics kit, never had an actual need to use them, and they're probably obsolete now anyways. There's better options, but you may still want to use it for whatever reason. So 78 is the series of integrated circuits that this belongs to. The next two numbers tells you the output voltage, so it's 0.5. We will get 5 volts out of this really reliably, and it is a pretty cool integrated circuit to learn about. It has temperature protections and everything. You really don't have to worry about accidentally damaging it. It protects itself, and so you can look at the data sheets for more info on that. Plus, I did earlier videos. I spent a lot of time on them, plus making the diagrams. They didn't get all that many views. So I'm just going to reintroduce the component, and I'll link those videos in the description. You can check them out. I took thermal images and all kinds of stuff. So in any case, let's get to it. The wiring is really simple. The voltage in, the input, is connected to the input right there. So I got an orange jumper there. Ground, the negative arrow, and that's going to be the ground for whatever load. All we're going to do is take multimeter measurements. And then output, I have this yellow jumper. So one thing you'll notice, you can add a heat sink. So you can add more metal to this so that it will cool off better. And I'll talk a little bit about that coming up. But make sure you can see that I'm inserting that. Pretty straightforward. There we go. So output down at the bottom there. Now, let's see. There we go. You can see the whole meter. I have my bench power supply powering the board at 7 volts right now. So it comes to this jumper. We come over to this jumper. It's 5 volts. So pretty straightforward. Now I'm going to just quickly turn the dial up. Now it says 13.8 on the display. And it's 13.8 right there. At the output, we have 5 volts. And there you go. Looks like it's going down a little bit. So looks like it might have took a little bit to regulate a tiny amount. But in any case, it's 5 volts there. Pretty much spot on. And so those two capacitors may have helped, but this is a simple circuit. We're just getting the straight voltages. So what's going on here is we are applying a higher voltage. So right here you can see the basic process. You give the integrated circuit here 7 to 35 volts according to one of the data sheets I read, and it gives you 5 volts out. Now the rest of that voltage, you have at least 7 volts. There's only 5 volts going out. What's happening to that voltage? Heat. It's being turned to heat. That's why this is obsolete for the most part. You may find a use for it, but you just got to be aware that heat is being generated. So I was only measuring the current with the multimeter. It doesn't take, or the voltage, I mean, it doesn't take much current at all. A tiny trickle, very small amount, has to go through the meter so that it can tell the voltage, but other than that it doesn't really pass any current. So this probably didn't warm up hardly at all. I probably could have touched it while it was running, but when more current's going through a load, it's having to break down that voltage still but provide more current. So this gets hot really fast. That's why there's this big metal plate on the back of the integrated circuit and a hole to screw even more metal onto it. So there's boost converters and buck converters. So a lot of my videos recently, we've been having to change the voltage. I'm using a battery pack, a portable power supply in a recent video, and the battery within it, its voltage is changing, and so there's probably a boost converter to take that lower voltage and put it to 5 volts and hold it to 5 volts as it's changing. It uses capacitors and inductors probably, or some other similar system, to just convert the voltage change into a current change. So in this case, a buck converter will take a higher voltage and lower the voltage, but it will take less current coming in because it's at a higher voltage. When it steps it down, it will also increase the amount of current coming in. There'll actually be more current going out than coming in, but it will be at a lower voltage. So the power will be the same if it is 100% efficient. So nothing's 100% efficient. So if you cut the voltage in half, you expect twice the current, but it'll probably be a little less than that due to losses. And then some of them may not even provide close to twice the current, but you should get more current if it is a boost converter, or buck converter I mean. And a boost converter will take a lower voltage in and output a higher voltage, but at less current. You'll have more current coming in, less current going out. This doesn't do that at all. The current coming in is I think the same as going out, but it's a higher voltage coming in, so that energy gets converted to heat. And so this wastes energy. It creates heat instead of changing the current. So I did other videos where I covered that in a lot more detail. This diagram was one of them. There's another diagram on the back of this that covered more, and I took thermal images and all kinds of stuff, so I'll link those in the description. If this component looks interesting to you, it's a good one to still learn about, even if you may never use it. And it is really simple. You just plop it in. So you may want to use it. You may just have one little thing that needs 5 volts, but everything's 10 volts or whatever. It doesn't take much current, so you accept the loss. And so it's a good component to learn about. So thanks for watching, and I will see you in the next video.